Hi, everyone. Thank you, Dr. Niebuhr. This is Chaopeng from Penn State. Can you see my presentation?
Yes, we can.
Okay, thank you. So the title of the talk is about going from parameter calibration to parameter learning. And I think there's a great deal of value to be had to attack different problems. A lot of these work are done by my PhD student Chaopeng Shen, postdoc Wenping Cai, and also visiting scholar Kai Ma, another PhD student Farshid. So I'm going to show some of these results here. I want to talk about the mighty potential that LSTM has shown, along with other deep learning models in hydrologic modeling. We have heard a lot this morning already from Gray's talk. I'm going to add something to it. Then we're going to address some of the issues and limitations with deep learning, more specifically small data environment. And what about variables that you cannot even observe? How can we tackle those problems? So first of all, before we start, I want to make sure that that hydrologic deep learning as a whole is actually on track to deliver the value, deliver the expectations that the society has placed on us. What does the society needs from us? We'll make sure that deep learning in the end, by the end game, can actually deliver on those things. One is that they want us to deliver long-term trends. For example, impacts of climate change. Want us to estimate human impacts. They want us to give short-term forecasts for disasters such as floods and droughts. We want to understand the impacts of hydrology on other systems, such as ecosystem and human water use systems. So some of the design goals for these models are, we need to quantify uncertainties. So not just giving one value, but the multiple values, like an error bands. We need to be able to incorporate human impacts. Sometimes there may not be big data. We have small data, and we need to estimate unobserved variables. So we need to achieve all of these things before I can claim that this path is a viable path. Okay. We also need to absorb near real-time data, okay, in order to improve our forecast. A lot of times we just want to understand the relationship between X and Y, right, from a scientific point of view. All right, so the case studies that I'm gonna show are two. There's one about soil moisture modeling, that we're modeling the soil moisture active passive satellite SMAP that was launched in 2015 and has a 2 to 3 day revisit time. So we learn from it to understand how soil moisture, especially the surface soil moisture, responds to climate forcings. The other things are streamflow modeling, and you have seen a lot of KMOS modeling, and we have expanded to 3,000 stations with daily data and company attributes. So the first paper that looked at soil moisture modeling, some of you might have seen this already. This was in 2017, where we looked at using LSTM. We train it to basically learn it from the dynamics of the SMAP satellite, train it in 1 year and test in the other year. In this test 1 year, we don't have any observations, okay? So it's a complete forward run. We have, again, a very high anomaly correlation of 0.9 across the vast majority of the CONUS of the continental United States. And we compare it with other models, including simple neural networks and autoregressive functions, regularized linear regression. So we get the highest anomaly correlation and also the lowest RMSE. Then we want to see whether this model, because anytime we're talking about machine learning models, we have this fear that it will not give us what we expect to happen in the future. So we want to see whether this model is able to capture long-term trends. And we did so by comparing the LSTM simulated soil moisture trend with the observed trend in the soil moisture probes, because the satellite wasn't that long to give you that trend. And as you can see, in these areas where, you know, this is x-axis is the in situ data, and where there's no drought, there's no big trend. LSTM also doesn't think there's a big trend. And when there's a drying trend, LSTM also captured on that drying trend. So in fact, we did this analysis for streamflow, and it actually is doing a much better job at capturing long-term trends. Even if it's captured, it's trained in part of the time series. The long-term trends were captured much better than some of the hydrologic models like SEX model. Okay. The second thing is short-term forecast. And normally you do this through data simulation. I just mentioned that. So when you have a model and you have an observation, this doesn't match with your model, so you adjust the model states, let it evolve until the next observation come in, then you adjust it again. So this is known as data simulation. You have to make a lot of choices for this scheme. For example, you're doing ensemble common filtering, you have to select which variables to include in the covariance matrix, how to solve the covariance matrix, how to do, most importantly, how to do bias correction. A lot of choices to make. However, this has become much simplified with machine learning. We actually put in the observations as an input item into the network through some kernels. You may or may not need to use kernels depending on what you observe. We find it to be useful in some cases and not useful in other cases. We call this data integration because it's not data assimilation. Okay, so we did this for streamflow, and it greatly elevated the Nash-Static Cliff coefficient. So without doing data integration, we are getting a median NSE of 0.75, which is already pretty good, pretty darn good already. At the top of the performance, it's very equivalent to the best models out there, STM models, and much higher than SEX model, which is here. If you do data integration, you get 0.86, which is really, really high, simulating the discharge from yesterday. So as you see from this CDF, you get this is SEXMA, this is the LSTM model, this is the DI model. So there's a clear separation between these two guys. And then we did this for soil moisture, and we had to actually run extra errands for soil moisture because the data there are gaps in the data and it's irregular, so we have to tackle that. But after some troubling this paper published earlier this year, you can compare our model, the error, with some of the other models that was kind of state-of-the-art model in the literature. The errors in the error-prone regions were reduced by a good 30 to 40%. Whereas in the rest of the areas, the errors are still also suppressed, although not as much. But overall, you're looking at like 15% if you're looking at a reduction in error, which is very good. And we actually tap into this model. We put together a tool within a week of time. And this website is here. So we put this together because there's a low-cost disaster at the beginning of the year. But the deep learning is really ready for battle. We commissioned it to predict soil moisture, and we gave this tool to actually people on the ground who are tracking soil low-costs. And then they were able to better track their low-costs. So this really has been in seeing some battles. All right. But another big thing with the streamflow is that you have reservoirs over continental United States. Reservoirs are a very tough problem. We looked at the NSE distribution for reservoirs. These are the red boxes are the large reservoirs. The blue boxes are the smaller reservoirs. And you can see there's a huge decline in the large reservoirs for irrigation reservoirs especially, and then hydroelectric and also fish pound. However, if you average across all these areas, we look at small basins with small reservoirs, we get a median of 0.77, somewhere around there. And then if your reservoir is large, okay, have a large reservoir, you get this line. And if you have diversion, that further pulls it backwards. So anytime you have diversion in large reservoirs, that tend to reduce your RMSE. But actually for the smaller reservoirs, it's actually better than the reference basins that don't have reservoirs. It's because the smaller reservoirs act as a buffer. Okay, and this work is currently under review. Another work that recently looked into is stream water temperature modeling. In fact, it turns out that NSM works perfectly for this case. We get a NSE of more than 0.98, and we actually took the residual. We subtracted the air temperature from the simulated stream water temperature. We still get an NSE of the residual. In the worst case, with the data scarcity group, you have 10% data in this black box, we still get an NSE of 0.92. So it's really capturing the variations, not due to seasonality alone, but due to groundwater mixing. All right, so those are what has already happened, right? I've spent about 10 minutes talking about what we have already done. But what is more interesting is this limitations between of so much of process of machine learning models. And here I have this. I used to have this convoluted slides, but now I'm kind of boiling down to a simpler slide. What are the limitations of machine learning? You know, we say wherever there is big data, it's like the luminous sun. Wherever there is big data, your wisdom big data saturates the soil. But we have places where there's no data or very sparse data. We have unobserved variables like evapotranspiration, groundwater, and deeper soil moisture and base flow that we just cannot supervise with machine learning. And machine learning cannot diagnose the cause and effects. And it's a little difficult to handle heterogeneity. Okay, so some of our recent work looking at sparse data regions. For example, in the world, you have camels, but you also have, you know, South America, Great Britain, you know, China that don't have that many data points. So we did a transfer learning technique where we used a model that was trained over camels and actually transferred into these different areas, Chile, Great Britain, and China. We see that a local model, which is the LSTM model trained on that small data set, compare that with a transfer learning model. And this transfer learning model is beating this, you know, for China's case, you know, if you have only 1 year of local training data, there's a 0.04 increase, but if you more data, actually the increase is even larger. For Chile, you know, there's a 0.1 difference. For even Great Britain, which has 600 basins, we also have a 0.05 of difference. So that benefit is pretty real and pretty substantial. And actually, we're talking about knowledge extraction. If we have more data in the source data set, for example, the camels data set, we can maintain a different amount of data in the camels data set and train the transform learning model. It seems like the bigger that source data set is, the better the transform learning model is. So this model is really extracting knowledge from your source data and migrating it into the unknown regions. And then we look at a set of regions where for a whole big region, you don't have any data, or you have very sparse data, or you have flow duration curves. I mean, this is a relaxed form of information. You don't have the daily data, but you have the distribution information. This is relevant for the future when you have satellite observations of streamflow. Okay, so this is the model that's trained over the rest of the continental US, but not inside this red region. And then we test in that red region. We give it the attributes. In the end, it give us, but we tried this integrating flow duration curves in here. And if we do that, we are actually able to pull up the NSE pretty substantially because of this migration of NSE. And if you don't use any attributes, this difference is even larger. So that means the flow duration curve itself already carried about the sufficient amount of information to approximate the effects of attributes. All right, so given the time constraint, I'm going to start chatting about variables that we cannot observe, and it's kind of the meat of this. We're proposing that to estimate the variables that we cannot observe, we're proposing to go from parameter calibration to parameter learning, okay? And my apologies for not being able to share all the technical details of this approach because there's some legal reasons for that. So I'll be simplified with the approach. So we basically have attributes that sort of serve as like a pseudo transfer function that goes into the surrogate model Vic, and then we supervise that learning, those parameters. So we calibrate the Vic model using this map data and then a scheme we call FPL. We need to rely on the process-based models, but the parameters is a huge pain, and we seek to solve this problem here. Okay, so I will pay more attention to the results, and my point here is to actually really get you interested in this. If you keep watching this, probably in the time frame of a few months before the AGU, the paper should be out, and you should hopefully should be out, and you should be able to see all the technical details of how this is done. But the results here are pretty surprising, very, very surprising. We compared the FPL machine learning supported parameter learning framework to SE shuffle complex evolutionary algorithm. As you can see, we have different kind of sampling densities for calibration. But always the SCUA will calibrate the model in about, if we put this as a functional threshold, in about 1,000 epochs, it gets calibrated, and then it's a slow decline. But for the FPL scheme, the more data you give it, see, there's different sampling densities. The more data you give it, the faster it converges and the better results it gets. So if you use an S4 calibration density, so that means so this means you have a 4x4 patch, and you pick one pixel out of there for your calibration, and you test it there. So then here it gets down below that. Even in the first epoch, it gets below that threshold, and then it can further. It very quickly goes beyond the lowest minimum value. So this saves you about 2 orders of magnitude. Okay, and then plus the circuit model saves you again 2 orders of magnitude. So altogether, we're talking about turning this parameter calibration for CONUS. That's a high performance computing problem for hundreds of processors, run it for 2 to 3 days. Now we can do it in one GPU over less than 30 minutes, okay? Approximately 30 minutes. So that's a gigantic change, and we're getting better results. And we're getting better results for the right reasons. So we did several tests. We're looking at a test on the neighboring cells. How much time do I still have? I think so. I still have 5 minutes, something like that. All right, we look at the neighbor cell. So we trained it in, this is a we call S8 sampling density. So we train it over 1 pixel out of an 8x8 patch. And we tested on this neighbor here across the diagonal, kind of far from the training point. And we test, we extend SCUA and FPL's parameters to that pixel. As you can see, the SCUA, when you test it, you know, this orange box is the neighbor cell, runs the neighbor cell. When you test it, it has a large bias, okay? It starts to generate a larger bias. But the FPL has a much smaller bias, okay? And then it also has a larger unbiased RMSE. So it's not just bias. The dynamics also deteriorated. If you look at the correlation dropped from like 0.6 to like 0.52, all right? So there's a big drop for SCUA. However, that's not the case with our machine learning supported FPL scheme. FPL scheme barely changed at all, right? So when you extrapolate it in space, it barely changed it at all. So that's a good sign. That's a good sign. What's even more interesting is this uncalibrated variable evapotranspiration. Okay, this is a variable that we did not invoke at all in our calibration scheme. Okay, so the model hasn't seen it at all. So we're comparing the SCUA versus. Whoops! Actually, I pasted this morning. I must have done this morning. Jesus. Okay. I have actually. So this model here is the FPL. So the FPL, when you compare it with the MODI-CT, it has a much smaller bias, and the correlation is about 0.78. I got NSE about 0.6. Okay, and we assess the ensemble. Actually, it's what's sitting here. I pasted the wrong figure. This is another version of the FPL. But if I paste the SCUA here, you're going to see a bias. You have to imagine this right now. Is around 60. Okay, around 60. The correlation is 0.6 something. NSE is 0.4. So there's a big difference between these two. And we think that the reason is after we use the machine learning supported FPL scheme, we're able to get at the right parameters for the right reasons. And if you look at the next picture, you will see why. Okay, the FPL generated parameters which are self-correlated in space, and the pattern kind of roughly matches our understanding of the hydrology of the aridity and as well as the mechanism of this model, VIC. Okay, the parameters for VIC is attached to the climate. That's how it works. But if you look at the parameters obtained by SCUA, it's a jumbled mess without any pattern. It's very mixed. It's very mixed, and there's a lot of noise. There's no pattern to it because you're really tapping into the equifinality issue. Okay? The equifinality issue is where the same parameters, they're very different parameters give you the same results, and therefore the parameter estimation scheme can kind of fly all around the map and give you all kinds of the parameter sets, and the parameters adapt to each other, give you the same soil moisture, but then the ET would be off. And all of the superior performance that we're getting is because we're getting the patterns right. We're posing a much better constraint than the SCUA. And we're completely changing the way this problem is framed. And I'm sorry, I'm trying to, like, we're not showing the details, but just kind of getting your appetite up here. But just hold on until a couple months, all the details will be out. Okay, so what we're showing here is the deep learning is, once we have this model, you can estimate all the parameters that the physical model can estimate. And we hope to actually improve the model as we go. So the deep learning model is helping us to address a major pain point in geoscientific model, which is parameter estimation. It's orders of magnitude faster, 4 orders actually, if you consider everything. It has better optimization results, which is surprising. It has better spatial generalization and better parameter behavior, and gives you overall better physics. And in a way, it completely redefined the calibration calibration problem. So with that, I stop here, waiting for questions. Thank you.
Yeah, thank you, Chaopeng. That's a very interesting presentation, and we do have several questions, and we have time for them. So the first one is, hydrologists have long used all kinds of metrics in model calibration. Why only NSE is used as a primary metric?
Yes, that's a good question. So not only with the NSC, well, actually we looked at RMSC, unbiased RMSC. I'm only showing you part of this. So I'm going to look at RMSC and in streamflow, we also look at KGE. But here, so you see, we'll look at bias. The bias shows the SCUA. When you do spatial extrapolation, it has a larger bias than the unbiased RMSC and correlation. Actually, we also looked at, the trends, how the trends was captured in the future, in decades to come, and it appears like, the machine learning model is doing better than SC-SAXMA for streamflow trends capturing.
Okay. Thank you. To potentially improve your predictions for reservoirs, have you considered assimilating satellite estimates of surface water extent?
That is a very good question. So I think it's definitely possible, and we should be able to do that. Very much similar to the data integration idea that we put in. The problem is you have to formulate the problem in a universal way. What I mean by that is, with a big data set, let's say hundreds of reservoirs or hundreds of basins with big reservoirs, you have to gather kind of the same data set with the same physical meaning, because a lot of times the data was generated, it has the same physical name, but it was generated using different programs or by different people, so they actually have different physical meaning, and so the kind of the machine learning model is trying to battle with that, there's some differences between the different zones, and it kind of fit it to climate attributes to kind of reduce that bias in the training data set, but in the test it will be off. But this is the reservoir work. We put in reservoir attributes into this model. So the capacity of the reservoirs, how far it is from the basin outlet, things like that. But I do think that if you for selected basins, if you look at a small basin, a small set of data, you want to incorporate reservoir size and volume, or the surface area into the prediction. It might work wonderfully. It might work, yeah.
Okay, and we have about 1 minute for a third question. The question is, I'm not quite sure I understand what exactly the transfer learning model is. Could you talk more about this?
Yes, so the transfer learning model, in there are two senses. One is parameter. Actually, we submitted this. It should be online very soon, so you can see the whole thing. There are two things. One is weights initialization. The other is weights freezing. So essentially, you train your model for CONUS. You get a set of weights, right? So it already initialized the model in a way that it's able to capture hydrologic dynamics. So the initialized model is better. But the next thing is you can freeze certain part of the model. So in this case, we tried different options. As you can see, TL, A, B, C here. You can freeze certain part of the model. You can freeze the recurrent part. You can freeze the linear input and output transformations. Or you can freeze other parts or partial part of the recurrent connections. And that way, you're basically freezing certain part of the functions. And then in a new target data set, you are kind of retraining it. You fine-tuning the model for the new target data set. The reasons because in the target data settings in China, for example, you don't have the same kind of attributes. You can't even train them together. Okay, so we have to do this. We have to resort to this transfer learning. And it turns out that you don't need a very good attribute data set to do this transfer learning. This is very valuable, actually. By this transfer learning technique alone, you can unlock deep learning based models for the vast majority of the world. If you have some streamflow gauges, just a couple of years, that can get your model calibrated, and you're going to get, start out to be very good, to have good results very quickly. So, yeah, it's exciting.
Okay, great. Thank you very much, Dr. Shen.